for this comic book or anything like that. Someone showed it to me at a conference I went to, and I liked the idea of it. Especially because polarity has often been something that my students really struggle grasping in terms of, yeah, they can memorize what's happening, but when it comes down to actually what understanding was lacking. So hopefully this will give us something we can always connect back to as we understand this concept of polarity. Okay, so I passed out the note packet. It's that bright orange one. Look at that for me, everybody. And there's a question at the top. Here's what I want you to do. If you're still working on the polar bears and penguins, just set it aside. As long as you were working productively, you're going to get points for doing it. You didn't finish it all the way. So, which all of you were working productively. So. Okay, there's a question at the very top on that orange packet that I wanted to answer on your own. You can earn a smiley face by doing so, which says, why do atoms bond? Write that down.
Where?
At the very top of the note, you see it there? Yeah. So tell me, why do atoms bond in the first place? All right, these 92 elements were created in the Big Bang. But since the Big Bang, they have then bonded in lots and lots and lots and lots and lots of different ways. Why do they do that? Okay, raise a hand, anyone willing to share their answer? Bryce.
I said they bond because by bonding they become more stable.
Good, so stability plays a key role in it. Good, have a smiley face back. Other ways to answer the question?
That's exactly what I was going to say.
Same thing, stability. Anyone else say something different?
You could also say I used to think of it like they look up to the noble gases, so they want to be a noble gas. And
Yeah.
So they're like, I'll do anything to be like that. You know?
Yeah, there's kind of this pattern of these full shells, right, of the noble gases creates that stability, right? That's kind of another way of looking at it, is they're going to share, trade their electrons, right, to get that configuration. Because for whatever reason, the way the world is created, that makes them chemically stable. Okay? Go ahead and give yourself a smiley face if you said something along those lines. Right, that means you get 2 because one right answer and then one right answer. Okay? What we're going to look at today is what causes the difference of why some share versus why some trade. Okay? And it goes back to that trend we learned last unit of electronegativity. Okay? Electronegativity is the force at which an atom pulls on electrons or attracts electrons to itself. And what we mean is it's not attracting its own electrons, it's attracting from another atom. Okay, how well does an atom attract electrons from another atom to itself? Okay, our general trend goes like so. Stopping at fluorine is the highest. And it is important to make a side note that these are just assigned values by scientists. It's not a measured value like ionization energy is, right? That's an actual, it has a unit attached to it. The numbers of these, you'll look at a chart later that has the numbers of electronegativity. Fluorine's has a value of 4. It doesn't mean anything besides a scale, okay? Remind your table buddy really quick in case they forgot. Why do the noble gases not have electronegativities?
Because they're not going to pull.
Yeah, they're not. They don't need it.
They don't bond because they're not bonding. They don't pull
Yeah.
Perfect. Okay, so this idea of bond polarity is it's a measure of how equally or unequally these electrons are shared. Okay, so once again, going back to the comic of the polar bears and the penguins, okay, the bond is polar when the electrons are not shared equally. The way I think in terms of connecting the word is polar means that there is poling going on in the atom. If it's non-polar, then it's not poling, and it's an equal balance. Okay? And it's all about that greater attraction for the electrons that it's bonded to. Now the extreme case is ionic bonding, right? Does everyone have that blanket I flipped to the picture? Okay? The extreme case is if it's so different in electronegativity, well then the penguin doesn't get any ice cream because the polar bear rips it away. Okay? Now, in this relationship, we result in, like what Isaac said before, a full-on positive and a full-on negative atom, which links together because positive and negatives attract. This atom is held together by the shared electron that's happening. You could kind of think of it as, in terms of like these little model things, right? Their orbitals literally overlap with each other and link. So for hydrogen, another way you could think of it is it's like this. So hydrogen has one little valence electron. Okay, chlorine has, that's not the best of circles. Okay, chlorine has 7. 1, 2, 3, 4, 5, 6, 7. They share, so now chlorine has its 8, and hydrogen has its 2. Because for hydrogen, 2 is stable, right? It doesn't need all 8. So that's kind of the difference. Versus this, where they're not actually lapped, but they're just linked through positive and negative charge. Now what happens though is when something is polar, the sharing is not equal. Okay, so for example, hydrogen and fluorine in the polar molecule. Fluorine has a higher electronegativity, so it's going to draw the electrons in the bond towards itself. The way we can indicate that is with a dipole arrow. The arrow points to the one with the higher electronegativity, and then on the tail of the arrow we put a plus sign. Any thoughts of why we would put a plus sign? Okay?
Is it the positive being pulled?
Close. If I'm moving these electrons, what happens to this side? It becomes positive, right? So versus, so the NaCl, right? This one gives up its electrons, so it becomes completely positive individually. This one is what we call becomes partially positive. It's not all the way positive because it hasn't given up its electron. It still gets to lick the ice cream every once in a while. But the electrons are hanging out on the fluorine side way more often. Okay, once again, this is known as a dipole arrow. The other way you can see it to represent this partial negative and partial positive is with this sign. So that sign means partially negative. And then you put another one for partially positive. Yeah, Zach.
Should you have been recording this lesson?
Oh, thank you. I did. I've been using my iPad because it gets me a better viewpoint. So it just sits back farther. But thank you. Always remind me. That's good. So. Yeah, Isaac.
Why is it not an ionic bond? Why is it a polar bond and not an ionic bond?
So it's all about how big a difference there is between the two values. Now there's an actual like mathematical equation which you'll do on your homework, but that equation is only helpful if you have a data table of values. So for example, just so you can see and kind of answer your question, Isaac, the electronegativity value of chlorine is 3.0. The electronegativity value of sodium is 1.0. So the difference between them is they have a difference of 2.0 of electronegativities. The general pattern is anything that is greater than a 1.7 difference is an ionic bond. Anything that falls between 1.7 and 0.5 is polar covalent, and then everything under is non-polar. So that's like the most technical way to identify the difference. It is just because this one pulls so much harder, it rips it off completely, so that they're not overlapped at all. It actually would be separate. Does that make sense, the difference?
Yeah.
The simple pattern is it goes down to if they're metals or non-metals. That's the simple without numbers of how you figure it out. Ionics are formed between a metal and a non-metal. Covalents are two non-metals. It's kind of simple. We'll kind of do some more practice with that as we go. Great question, Isaac. Have a smiley face for that. what we can also do actually with those differences in electronegativities is you can measure what's known as the dipole moment, which in a sense tells you how strong of a pull is happening. The stronger or the larger the dipole moment, the more polar the bond. So once again, when we talk about this idea of dipole moment, we're talking about a shift of electrons one way, resulting in a negative side and a positive side. If something has a very low dipole moment, then it's a very small shift. And I'll show you, let me pull up this simulation to hopefully give us a little visual here. Okay, so if two atoms, so this, what I'm going to do is put on what's known as the electrostatic potential. So red is negative, blue is positive. So the higher the electronegativity of one, it's right on that bar that I can't see, there we go. The more drastic of a negative and positive side that we get. If it's too drastic, then technically that bond would, in a sense, break and not be covalent anymore. Okay, what's interesting, let's get some real looking molecules here. Let's get water, for example. Okay, Isaac asked, if any else of you are wondering, we'll learn in a few days of why water looks like this. One of the big things in this unit is we're going to learn how to draw these shapes in 2D and then predict their 3D shapes. But this is what water looks like. And here's its electrostatic potential. So with water, we get a positive on this side, negative on that side. Let me rotate it in 3D space. And this is, in a sense, we'll talk more about it, but this, in a sense, is why it hurts if you belly flop into a swimming pool. Because this little water is like a magnet. It has a negative and positive side. All the other waters around it are also like little magnets. So what the water is doing is the water's playing a game of Red Rover against you, and you hit the swimming pool. Now, it's not, so here's a water, right, and it's going to be attracted to like another water. Like so, right, so there's this force of attraction right here. Is that a chemical bond? No, it's just this is positive, this is negative. That's why we can break it, right? If you jump in the right way into a swimming pool. But if you don't and you don't break that tension, you can literally feel the force of the molecules. Yeah, Ed.
Is that why water stays in like droplets?
Yes, exactly. Same reason why it does a little like bead, right, little ball, is because they're holding on to each other and creates that surface. Yeah, no, good connection.
I was wondering why it doesn't form like an ionic bond. Because you know how they have like a difference of charge? And
So ionic would be the process of actually completely taking the electron away from the hydrogen. So they're still sharing it. So that's why as a whole, it's not a separate positive and negative thing. Does that make sense, the difference?
yeah, I was wondering about the connection between two different water molecules.
Oh,
Yeah,
like
yeah,
this to
does that make
this.
sense? Yeah.
That's a great question. The best way I can answer it right now, then I'll think of if something else comes to mind.
Because oxygen is pulling pretty hard, right?
It is, yeah, it's a pretty strong difference in electronegativities for sure. But it kind of goes back to the sense that they're still just partial things. This is still just a partial negative and a partial positive versus like an ionic, which is full on negative and full on positive. But yeah, great question. Max?
So, just for an ionic bond, how come those are stronger than like the attraction between like two water molecules, for example? Because it seems like it would be similar to me. Because like, for example, if it was ionic and one molecule had all the electrons. And
Yeah.
It's attracted like a magnet kind of. Then how come the bond between like two water molecules isn't the same?
Isn't as strong? Great question, and it goes down to the difference of the ionic is an actual chemical bond because the electrons have been removed from one, right, from sodium and sent to chlorine. This is not a chemical bond. There's no transfer of electrons happening between one oxygen and another one water and another water. It's still a force. We're gonna learn it's actually called an intermolecular force. There's two types of forces. There's intermolecular, meaning between two molecules, and then intramolecular, which is within the molecules. So an ionic bond is the force within it, which is very strong because it's an actual bond. This is a force outside of it, which still is decently strong when you consider what it can do, but it's not to the same strength as the actual chemical bond.
Okay,
Does
so
that kind of make sense?
it makes sense. I guess the only thing that I'm still a little confused about is what makes it like a bond rather than just an attraction.
Okay, it's the actual movement of the electrons. In an ionic bond, right, when sodium bonds with chlorine, sodium is giving up, so here's our sodium, right, here's our chlorine. Sodium is giving its electron completely away, and so it is fully positive, like the whole entire thing is positive. And the chlorine is all negative, right? Within this molecule, the electrons here are being shared. They still belong to hydrogen, they still belong to oxygen. They're shifting one way, so they are on this side more often, making it a little negative, but it's not a full-on negative.
Okay.
Does that make
makes
sense?
perfect sense.
No, great question, great question. And that's kind of, it's cool to see the connection between how the bonds are similar, but it's also important to recognize like how they also are different from each other. So, any other questions on that for now? Okay, go back to your notes and let's fill in this little table comparing our three types of bonds. Okay, so in a covalent bond, the electrons are shared between two atoms. Once again, if you want a picture, right, a visual, you're a visual type person, the idea of these orbitals. I'm not using coordinates, should get told you for it. Right, the orbitals actually overlap with each other. Two of the electrons in this case get shared. So everyone is content. Keep in mind with covalent, you have two types of covalent. You can have polar covalent, where they're not shared equally, and you can have non-polar covalent, where they're shared relatively equally. Well, I should have showed you on the theme the 3D picture of a non-polar one. I'll put one of those up in a second. Okay? Covalent molecules are formed between two nonmetals. At least this is how you do it when you don't have a chart of data. Okay? So a nonmetal with another nonmetal will always form a covalent bond due to the fact that they have high electronegativities. Neither atom is willing to give up its electron. So they just compromise and they share their ice cream instead. Okay? Ionic is when the electrons get transferred once again where the sodium is actually giving its electron away, and then they're held together through a full-on positive and full-on negative charge. And this happens between a metal and a non-metal. The reason being, once again, going back to electronegativities, is non-metals has high electronegativities, metals have low. And so it just rips it off the other one, or lets it go. Okay, now metallic bonding, this is an interesting one. First off, you can probably guess it's formed between metals, right? Hence the name. So when a metal bonds with another metal. Okay. What type of electronegativities do metals have?
No.
Low, right? So none of them are very inclined to pull more electrons to themselves. They're actually all fairly willing to just like let theirs go. So what we get is it's kind of a combination of both the bonds in a weird way, where we get shared electrons, but it's between all of the atoms. The analogy or the way they often describe a metallic bond is they call it an electron sea. So here's kind of, if we could zoom in and actually see it, it's kind of what it would look like. You have a bunch of positives. So these are the atoms. And they're positive because they've given up their valence electrons. But unlike covalent, where it's just like, okay, I'll give to you and you give to me, they just share them with everybody. They often joke that metallic bonding is like communism.
That's what I was gonna say.
Where it's just share with everyone. So in a sense, this right here, this is our electron sea. The negatives just flow, and they're not really attached to just a single one, but because there's positive and negatives, it holds together. Now what's really cool is connecting, once again, this is where our lab next time, like real lab time, finally happening. I know we haven't had them yet, so it's like exciting. Well, hopefully you're excited. I'm excited to get in the lab. But the properties we see of metals can be explained by their structure. One of the common properties of metals is most metals, some take more force than others, but most metals you can change their shape, right? Obviously there's some strong metals that you have to use more force, but you can hammer them and shape them, right? The reason why metals are so malleable, that's the technical word for shaping something, is because of this electron sea. It's not a rigid bond, it's a very flexible type thing that can happen. Ionics, those are our salts. Is salt malleable?
Really brutal.
No, very brittle, right? Because, think of its structure, right? Positive, negative, positive, negative, right? Negative, positive, right? It's very resistant to just bending, it just, in a sense, breaks instead. And then covalent, you see a combination of both, depending on what it is. Some of them are quite malleable, others are not. Once again, but it all goes down to the structure of them. Okay, any questions? Okay, let me pass out to you your homework packet. And I'll explain. So there's our homework for tonight. So 2.1a and 2.1b. And once again, it looks like a lot, but the time it takes to do each of those individually shouldn't be too long.
So for
Is
the
this our
reading,
note packet?
reading, is it 486 and 495, or what's the?
Yeah, 486 through 495.
I like this color.